All right, great to see this great turnout this evening for our Space Talk for March 2023. I'm Mike, the Planetarium Director, and this is our regular series that's happening on the first Thursday of every month. Our April 6th Space Talk is going to be Dr. Price Whelan of Flatiron Institute talking about galaxies. But I'm really excited tonight to introduce Dr. Marc Favata from Montclair State University. He is a local person, and we'll talk about that a little bit during our program, and got his undergraduate from Caltech and then went to Cornell for his PhD. He's also done prestigious visiting scholar visits to a number of institutions. Now, his area of expertise is a really exciting development in the field of astronomy, looking at gravitational waves, how we learn about them, how do we detect them, and how they can tell us interesting things about the universe. So I'm going to hand things over now to our wonderful presenter, Dr. Marc Favata.
Thank you, Mike. Everybody, how you doing? We ready to learn about gravitational waves tonight? All right, let's get going. So what's my goal tonight? My goal is to teach you a little bit about gravitational waves and what are they good for, okay? And essentially, the answer to that question is they are providing us with a new way to observe the universe. I want to start off, though, with some pretty pictures. So can we cue the first set of slides here, right? So when we think about astronomy, what do we usually think about? We usually think about those beautiful pictures you've seen in prior decades from the Hubble Space Telescope, and now in the news you've seen these beautiful pictures from the James Webb Space Telescope, which is what you're seeing now. Here you're seeing the Carina Nebula, one of the first pictures released from the James Webb Telescope. So next slide, please. And you've seen lots of other pretty pictures over the years. Here's another James Webb showing the Southern Ring Nebula, showing some gases which have been expelled by some stars in the center of this nebula and then are being irradiated by those stars. Next slide. Here we see a very lovely picture also by the James Webb showing a cluster of galaxies. So this is a conglomeration of many, many galaxies. Every little smudge you see here, except for the very bright things with spikes, everything else is a distant galaxy. In a very localized region, there's a whole bunch of dark matter in here too that you can't see. But it's another very beautiful image from the James Webb. Next slide. Next slide, please. And we see the dark emptiness of space. Hopefully we'll see something else. We had it. We had a nice galaxy, and now the dark emptiness of space again. Okay, here we have a beautiful galaxy called the Tadpole Galaxy. This is a Hubble Space Telescope image where you're seeing really a smaller galaxy colliding with this larger galaxy, and it sort of has stripped out some material during an earlier phase of that collision. Next slide. Here we see something closer to home. We see our sun, and we can see these big loops of plasma, which are essentially tracing out loops of magnetic field that are coming out of the sun's surface. This is an ultraviolet image taken with the Solar Dynamics Observatory. Next slide, please. And here we have Saturn. This is an actual picture. It almost looks like it's computer generated, but this is a picture from the Cassini spacecraft showing Saturn and its rings, and you can see the shadow of the rings on the surface of the planet. Next slide. And here we can see, what we often think of as telescopes. So all those pictures I just showed you are taken with light. They're taken with some form of electromagnetic radiation, whether it's optical light, which you might see through a backyard telescope, something seen with a more sophisticated telescope like the James Webb or the Hubble or the Keck telescopes in Hawaii. But we can also take images using ultraviolet radiation, using infrared radiation, using radio waves. Here we have some radio telescopes. But all of these things are still the same It's the same thing we're looking at. We're looking at light. We're just looking at different frequencies of light. Just like there's high frequencies of sound and low frequencies of sound, it's still the same thing. It's still sound. In this case, it's still light. Okay, but what if we could use something completely different to observe the universe? Something that's not light. What if we could use gravity itself as the means to observe the cosmos? Okay, that is what we're trying to do with gravitational waves. So next slide. So let's talk a little bit about gravitational waves. So what are these things? The gravitational waves are ripples in the geometry of space and time. So Einstein came up with this theory of relativity, which basically gives us this picture of space and time as being this kind of fabric that makes up the universe, and heavy masses perturb that fabric. And just like if I throw a stone in a pond, I disturb the surface of the pond and it sends out these ripples or waves throughout the pond. In the same way, if I have a heavy mass and I jiggle it around, it also will send out waves, but it will be waves of gravity. The gravitational field itself wiggles, and it sends those wiggles out through the universe. And those wiggles propagate at the speed of light, but they're very hard to generate. To make something that produces detectable wiggles in gravity, we need very dense concentrations of mass or energy moving at very, very fast speeds close to the speed of light. So it's difficult to detect these gravitational ripples. I want to explain a little bit sort of a point that's going to be important later to understand how we detect them. So next slide, please. So let's imagine that I have this gravitational wave that's pictured here in red. Imagine it's coming directly out of the screen towards you. And imagine we have this ring of, I think of it as a ring of ping pong balls floating in space, and they're not tied together, and they're initially in a circle. What the gravity wave will do to that ring is make them oscillate in the way that's pictured here. Okay, and this phenomenon of what does a gravitational wave do when it interacts with material is going to be important to discuss how we detect gravitational waves. So you can see basically the pattern is it's sort of, it pushes them in, and then these ones go out. These ones come in, but that one goes out. That is the basic pattern of what a gravitational wave does when it pushes on things. So next slide. So what do we see with gravitational waves? Well, there are several different things we can see, but in terms of what we've seen so far, our main sources, meaning the objects that we are trying to observe, are things like black holes. That's our main thing that we're trying to see, but there's other things I'll talk about. So what is a black hole? I can think of a black hole as basically a region of space and time in which I can go into it, but I can't come out. Okay, that's sort of the simplest way to think of a black hole. I can go into that spherical region and never get out again. How do I get these black holes? Most black holes we think are formed from the end states of massive stars. So when heavy stars burn up all their fuel, when they're finished converting hydrogen and other elements into even heavier elements, essentially the star's thermal pressure can no longer support the weight of the star, and if the star is heavy enough, it will collapse and form a black hole. Next slide, please. The other main objects that we're interested in observing are neutron stars. Neutron stars are another stellar end state. They're another result that can happen after stars die. Neutron stars are essentially an object that has about the mass of the sun, but is about as big as, I don't know, where are we here? This is Queens, I guess. This area of New York, okay, they're around 20 kilometers wide or so, 20 to 30 kilometers wide. So think about all the mass of the sun put into something 20 kilometers wide. So they're also very dense. They're basically as dense as the nucleus of an atom, which maybe you might not have thought of as being very dense, but is in fact extremely dense. So it's essentially a gigantic atomic nucleus in space. Next slide. And so what we're trying to observe are really pairs of these objects, binary star systems composed of two black holes, two neutron stars, or a pair of black holes and neutron stars. And how do we do it? Well, we need a telescope, but our telescope doesn't look like those other pictures I showed earlier. It looks like this curious device, or set of devices, which are called laser interferometers. So if we look at this particular object here, it's this big building with these big concrete tubes. And here you can see another picture of of one of these concrete tubes. And inside this concrete enclosure is another steel tube that is under a very strong vacuum, meaning there's very little air inside at all. And there's a laser beam going inside these tubes, okay? And there's mirrors at the ends of the tubes. And I'll explain in a moment how we can use this essentially physics experiment to detect gravitational waves. So we have a couple of these detectors. We have the two what are called LIGO detectors. Let me see if I can see them. There's one here in Louisiana. There's another one over here in Washington State. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. And here you can see what it looks like inside the building. Again, it's this big vacuum chamber, and there's a laser beam that's sort of bouncing inside of these tubes. And there's all this complicated optics, and there are these mirrors that are suspended on these glass fibers. And that's what the gravitational wave is shaking, and I'll explain in a moment how that works. And in addition to the two LIGO detectors, there's also another similar detector called Virgo, which is very near Pisa, Italy. And there's a fourth detector in Japan called Kagra, which is underneath a mountain in Japan, where there's several other physics experiments located as well. Next slide. So how does a gravitational wave detector work? So in a simplified version, I have a laser beam, I have a beam splitter, and I have the two mirrors that are hanging. The mirrors are like the little white ping pong balls in the previous diagram we saw. And when the gravitational wave passes by, it's shaking those mirrors. Those mirrors are free to shake back and forth because they're suspended by these wires. And the laser beam, it's sort of running a race down the two arms. And if the arms are not jiggling, then the interferometer is set up so that when the laser light combines back onto this photodetector, it undergoes a complete cancellation, something called destructive interference. But when the gravitational wave pushes one mirror out and the other one in, it causes the path that the two light rays travel to be a little bit different. And that means when they line back up at the photodetector, they're undergoing this oscillation. Sometimes they cancel out, but sometimes they add up, and I get a bright spot. So I'm looking at this, so I'm producing this fluctuating bright and dark spot as the mirrors are being shaken back and forth by the passing of the gravitational wave. Okay, so that is the fundamental principle we're using to observe these waves. Now, the actual device, of course, is vastly more complicated. You know, you spent about $1 billion of your hard-earned taxpayer dollars constructing these two devices. And the reason it cost $1 billion is because it's really hard to detect these gravitational waves. The waves are very weak, and they are moving the mirrors by a 10,000th of the diameter of a proton. A 10,000th the diameter of a proton. It's an extremely, it's the most precise measurement that basically we can do. It's the equivalent of measuring the distance to the nearest star to within the width of a human hair. So it's an extremely difficult measurement to do. And as you might imagine, there's lots of other things that can shake the detectors more than that gravitational wave. So a lot of the work goes into isolating the detectors and accounting for all the various sources of noise that can also shake the mirrors. Next slide, please. So the LIGO project is not just these detectors, it's really a group of people that do all the work. So it's a big scientific collaboration with over 1,500 scientists and students across many, many countries. And they've been working on this project for a very long time. And also been working with their partner observatories, the Virgo Observatory, and now the Kagra detector, which has finished construction in the last few years. Next slide. So what did we find? So the journey to detect gravitational waves is a very long and interesting discussion, but the punchline is Albert Einstein came up with this idea that gravity should have waves back in 1916, a year after he came up with his theory of relativity, of general relativity. And people thought that, you know, basically there was no hope detect these gravitational waves because they were so weak. In the intervening century, there were various attempts to detect gravitational waves. There were even claims that they were detected, but those claims turned out to not be true. And eventually, we had to wait for this LIGO project to undergo not only its initial construction and observation period, but a major upgrade to make the detector more sensitive. And shortly after that upgrade was complete and the new detector was turned on, within a very short period, we saw these two signals, which you can see in red and blue, in the two detectors, the one in Washington State and the one in Louisiana. And what you're seeing here is a combination of the noise in the detector that's been filtered out to some extent and the actual signal of the gravitational waves in these two wave patterns that you see here. And if you shift the patterns a little bit, you see that they line up on top of each other, okay? Meaning both detectors are seeing the same thing. Why do they need to be shifted? Because the gravitational wave travels at the speed of light, and it takes time for it to travel from Louisiana to Washington State, and if you shift it by the appropriate time, they line up very nicely. So this is really what we call the first detection, the first event, and it goes by this name, GW 150914. This just means the date that we observed it in 2015 in September 14th. Okay, so you'll see this number show up in the next couple slides. Okay, and this was a major discovery because it's the first time we ever were able to detect gravitational waves. Next slide. So what did we see? What was that detection? That detection was the merger of two black holes, and that is what you are seeing here in this numerical simulation, which essentially is putting Einstein's mathematical equations on a supercomputer and solving them. And so here you see the two black holes. You see the event horizons of the two black holes. You see the orbit that's being traced out. Here you're seeing a representation of the curvature of space and time. And on the bottom, you're seeing the gravitational wave signal. Okay? And we see that the black holes, as they're emitting these waves, they get closer and closer together. As they get closer and closer, they orbit faster and faster. And at the very end, the simulation's being slowed down here because this all happens super fast. They merge together and they form a single larger black hole. And that black hole has some distortions which sort of get radiated away. Just like if you strike a bell, the bell eventually rings down and becomes quiet. And those waves then get transmitted, just like the stone thrown in the pond. Those ripples get propagated throughout the rest of the universe, and many millions of years later, they enter our detector. So what did we conclude from that first event? Well, that first event, that first detection of gravitational waves, was the first time we ever saw two black holes merge together, and it actually provided the best evidence that black holes exist. There was a lot of other really good evidence for black holes before that, but this sort of sealed the deal on black holes being a thing that are exactly as predicted by Einstein's theory. From that details of that signal, we were able to tell that the masses of the black holes before they collided were 36 times the mass of the sun and 29 times the mass of the sun. Those are the masses of the two black holes. This sum adds up to 65 times the mass of the sun, but we can also tell that the black hole that was formed from that collision had a mass of 62 solar masses. So there's a difference of 3 solar masses. Where did that 3 solar masses go? That 3 solar masses went into the gravitational wave energy. So this process essentially converted 3 solar masses of energy into gravitational wave energy, which then got propagated throughout the universe. So if we convert that amount of energy released in the amount of time for this event to occur, it ends up being an extremely bright event, bright in the sense of gravitational waves. It's the equivalent of converting 200 suns worth of energy in 1 second. Okay, so take 200 suns, convert all of its mass into energy in 1 second, and that is the brightness of that event. It's equivalent to the steady luminous output of 100 billion trillion suns. It's 164 billion times brighter than the brightest supernova and 10 times brighter than the combined light of all the stars in the observable universe. So it's an enormous amount of energy, but it produces no visible light. You could be looking right at it and you won't see a thing because all of that energy is in this gravitational wave energy. Next slide, please. So this discovery was a big deal, and it very quickly won some of the founders and leaders of the LIGO project the Nobel Prize in 2017, because it was essentially this, final piece of Einstein's theory that was not yet confirmed. And this discovery confirmed that these gravitational waves do exist. Next slide. So what I want to talk about next is I want to make the connection between gravitational waves and sound. Now, gravitational waves are not sound. They're ripples in gravity. Sound is an oscillation of air molecules, so it's a different phenomena. But gravitational waves are very much more like sound than they are light, okay? And our detector is very much more like a microphone than it is an observatory that takes pictures, okay? So when we're detecting gravitational waves, we are in a sense listening to the sound that the universe is making. And so the kind of picture I want you to have in your head is when we think about light, we're really, a lot of what we're observing is stuff that's hot, and that's emission that's really being produced at an atomic level. But when we think about sound or gravitational waves, we're really thinking about a disturbance that's produced on a more macroscopic scale. So for example, if I play a drum or a musical instrument, right, the thing that's shaking is either the surface of the drum or the string of the musical instrument for, say, a cello or a violin. So that's a large scale thing that is vibrating back and forth. But when I look at the cello or the violin, I'm looking essentially at light being reflected from the instrument at a microscopic scale. So the sound is telling me something with a big scale, but light is telling me something at a microscopic scale. So next slide, please. So to give you an idea of how we detect these gravitational waves via analogy with sound, I want to show this little animation, which basically illustrates how we're able to pick out this very faint signal from this data. Remember I said that the gravitational wave is shaking the detector by 1/10,000th of the diameter of a proton. So what you're seeing in black here is essentially the noise in the detector. And there's some signal that's embedded in that noisy output. So that's like the flashing output of the photodetector. And in purple is a template. So this is a possible signal that we're looking for in the detector. And essentially, the trick of detecting gravitational waves is we're computing a kind of number by comparing this template against the data. Okay, and when we line up the template with the data in the right position, such that the template is lined up with where the signal is, then this number that we calculate, called the signal-to-noise ratio, is going to get large. So please play the animation. Right. So you see this template is essentially being slid past the detector output in black, and there's this number that's being calculated, but it's a small value. It's like 2. 3, 4, it's a small number, but right there, it jumped up to a big value like 10. That means at that spot, at that time value, we found something, okay? So that's the basic idea of how this detection of gravitational waves work, is we have to create a template. We have to have some idea of what we're looking for, and we have to try lots and lots of different templates and slide them around the data until we find a good match. It's kind of what we call a template matching type problem. Next slide, please. And so these templates are, we can think of them again as being analogous to a sound signal that's generated. And the details of the sound signal encode in it properties of the object that we're looking for. Much in the same way that when you listen to different musical instruments, the frequency or pitch of the instrument is produces a different sound and telling you something about the instrument. And one analogy that sort of will help us understand this is if we have an instrument like a tuba, right? That's a really big instrument, right? A tuba plays a low frequency sound, right? But a smaller instrument, like a flute, which is much smaller in size, plays a higher pitched sound. Okay? So the size of the instrument is related to the frequency of the sound. And the same thing holds for these black hole mergers that we're able to see. So that first detection, right, this was the first event that we saw, was a relatively large pair of black holes whose total mass was around 65 solar masses. And if we play that signal, converting it to sound, it sounds like this. Okay, it's this very low frequency whoomp type sound. I'll play that again. And it's relatively short. It doesn't last very long. Really, the system has been going on for a very long time, but our detector can't see to arbitrarily low frequencies. It starts listening at around 30 hertz, and then it ends depending on the frequency where the sound stops, or in this case, where the black holes merge together. And for very massive black holes, they merge together at a relatively low frequencies because big things are associated with low frequencies, and smaller things are associated with higher frequencies. So if we now look at a different black hole system, so I think this was the third object that was discovered. Like this one goes a lot longer. And this object, by looking at the template and seeing which template matches well with the data, we were able to conclude that this black hole has this pair of black holes has a mass of 21 times the mass of the sun. And if I play that sound now, right, we see that it went to a little bit higher frequency and it lasted a little bit longer. So let's compare the two. So this is the first one, the heavier one. And this is the other one. So you can see the pitch was higher, right? And that's essentially the combination of the pitch and the duration is how we can extract information about what is the mass of the whole system and the individual masses of the two objects. To give you a more extreme example, one of the most important events we detected was the collision of two neutron stars on August 17th of 2017 from the designation here. And this event, because the masses are so much smaller, the total mass is 2.7 solar masses, this event goes to a much higher frequency and it lasts very much longer. And you'll see how dramatically different that is. So please play the next slide. So you can hear this really low rumble, right? I think you can all probably hear that. And so these are now these two very lightweight neutron stars orbiting in a relatively wider orbit. And the orbit is just like the animation we saw of the two black holes, slowly shrinking with time. And as it shrinks, the pitch is getting higher and higher. Because these objects are smaller, they're able to get closer and closer to each other, much closer than the two heavy black holes are able to get. And you can hear the pitch getting higher and higher. And then they merge together at the very end, reaching a much higher frequency. So from the details, the duration of that signal, the frequency it goes up to, the details of how the frequency evolves with time, we are able to extract a lot of information from these events. Next slide, please. So there's all sorts of other information we can extract from these events. Here we have a simulation put together by one of our Montclair State undergraduate students, Michael Giantana. And what you're seeing here is a little black hole going around a larger black hole, but the larger black hole is spinning very rapidly. And the spin of the black hole essentially forces, it's sort of causing the swirling motion of space and time around the black hole. And that's causing the orbit of this particle to not stay in the same plane. The plane of the orbit is undergoing what we call a precession, where I can imagine I take a flat plane, but then I rotate the plane. Right, it's undergoing that kind of motion, and that's caused by the fact that the larger black hole is spinning rapidly, and this effect of the precession of the plane of the black hole's orbit itself imprints a modulation on the gravitational wave signal, which we can pick out if I now play the sound corresponding to this signal that you see here, and you can see that there's already some kind of extra modulation on top of the signal. So let's play that one. So you could hear that it had that chirp where it goes whoop, but in addition to that, it also had this whoa, 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 this extra modulation on top of it, which is a signature of this spin precession. Next slide. Another effect we can try to pick out is the orbit circular or is the orbit eccentric, meaning like it looks like an ellipse shape or an oval shape. Okay, so here we can see the sort of the total orbit, and here we see the sort of animation of the orbit of the little black hole going around the larger black hole. And we see that this orbit, you know, it moves quickly when it gets close to the larger black hole, but the shape of the orbit itself is undergoing a different kind of precession, where it's as if I took the ellipse shape and I started to rotate the ellipse shape, but in a different way than the kind of precession we saw previously. And so this signature of the eccentricity will also impart an additional kind of effect on the wave signal, which you can kind of see here. And it's going to impart a kind of a knocking sound, which we'll hear. So here you heard this, in addition to the overall chirp, this increasing frequency with time, this whoop, superimposed on top of that, you heard this bump, 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 right, which is essentially due to the little black hole coming really close and swinging by really quickly when it gets close to the larger black hole. Okay, and that's something that we would only see if the orbit is eccentric. So you can kind of get a feel of how aspects of the signal, which we can convert to sound, let us infer information about the actual physical system that we are trying to observe. Next slide, please. So what have we found? Okay, so over the so the LIGO and Virgo detectors, they ran for about 5 years, and this sort of summarizes what we have found so far. So before I say what we found with gravitational waves, I want to show what we knew about black holes before. So shown in this sort of pinkish color over here. So what you're seeing are different dots. Here, these dots represent black holes. And what's plotted is the mass of those black holes in units of the mass of the sun. So these are all of the black holes in the range between 1 and 100 solar masses that we knew about using electromagnetic waves. So using, you know, mostly X-ray telescopes, but also some optical and other wavelength telescopes. So this is like in all of astronomy, in all the history of astronomy, these are excluding the really heavy black holes that are millions of solar masses, these are all the black holes that we found, okay? These are all the black holes we found in just 5 years with gravitational waves, okay? And the way to read this plot is, you know, I had this black hole of this mass, a little over 20, merge with this black hole, let's say a mass of around 50, it merged to something that's like, you know, 70 or 80 solar masses. So these two merge with this one here. So you can see there's an enormous, just in 5 years of observation, we found a huge number of black holes. And not only did we find a huge number, but we see them in a mass range that's much higher than the mass range we observe with the ones we saw with electromagnetic observations. Next slide, please. So a couple of highlights of what we found, in addition to just the sheer numbers. So we found about 90 gravitational wave events so far over those 5 years of observation time. One of those events was particularly massive. So this is the first detection that we talked about earlier, a 29 solar mass and a 36 solar mass, producing a 62 solar mass. But we also found one that was quite heavy, a 69 solar mass black hole merging into a 95 solar mass black hole, producing a 156 solar mass black hole. This now gets us into the regime of what we call intermediate mass black holes. This is a region of black hole masses between roughly 100 to a few tens of thousands that we had some hints of evidence for, but never before did we have really firm evidence for this category of masses. So LIGO is starting to open up to us the ability to observe this much heavier range of black hole masses. Next slide. The other pretty major discovery that LIGO made was the first observation of two neutron stars colliding. So for many years, we've seen many systems of two neutron stars orbiting each other, but those were in very wide orbits. We never saw them so close that the orbits could collide together and produce this enormous explosion. Okay, and this is what we observed in August of 2017. We saw these two black holes collide together. We saw the signal with gravitational wave telescopes and with many, many different kinds of electromagnetic telescopes. So this event was really opening up to us a new way to do astronomy where we're combining information with both gravitational wave observatories and electromagnetic observatories. It's the only event that we've been able to see so far in both light and gravitational waves, but we hope that when LIGO starts running again in a few months, and it's going to run for another 18 months, we hope to detect more of these events where we see them in both light and gravitational waves. Next slide. The other major discovery that we made is the first observation of a neutron star orbiting a black hole. So people theorized for a long time that just like you have black holes orbiting black holes and neutron stars orbiting neutron stars, you might also imagine that you could have a neutron star orbit a black hole. But there was never firm evidence of this kind of system, but LIGO and Virgo provided the first evidence for these kinds of systems. Next slide. So what are we trying to do with these observations? What are the big questions we are trying to answer? So here are a couple of those questions. First, we want to know how many of these black holes are out there. Can we take a census, essentially, of the black holes that are in their universe and learn about them? What are their masses? What are their spins? How did they get to have those masses and spins? And we could ask the same questions of neutron stars as well. And we could also ask questions like, what are the insides of neutron stars like? That may shed some light on aspects of nuclear physics that we're not able to probe using our laboratories here on Earth. Neutron stars are also important because they are one of the ways that we can make heavy elements via these neutron star collisions. When these neutron stars collide at these enormous speeds, they produce new elements on the periodic table. So it helps us fill in our knowledge of where do all the elements on the periodic table come from. We can use these collisions to also measure the expansion rate of the universe. And ultimately, we use these collisions to test Einstein's theory. We think that at some level, Einstein's theory must break down because Einstein's theory of gravity does not mesh well with quantum mechanics, our other key theory of physics. And perhaps these gravitational wave observations can provide some hint of where Einstein's gravity breaks down. Next slide. So what's coming next in this field? So we've observed black holes colliding, we've observed neutron stars colliding, we've observed pairs of black holes and neutron stars. We expect to observe a lot more of these events. We hope that we might also see a supernova explode in our galaxy. Okay, that's a very rare event, maybe once or twice per century, but if one of those happened very close by, we might detect that with gravitational waves. We might see a single neutron star that has a little bit of a bump or deformity on it, and as that bump spins around really quickly, it will also produce gravitational waves. That's also very difficult to see. Or we might see something completely unexpected. So we're just going to have to keep observing and see what happens. Next slide. The other thing we're going to be doing is observing with more detectors. So we have the two LIGO detectors. We have that Virgo detector I talked about. The Kagra detector is brand new and is going to be joining the search this summer. And there's also an effort to build a third LIGO detector in India. And so once we have a network of observatories operating, we're going to be able to detect even more of these black hole and neutron star collisions. Next slide. We also have other ways of detecting gravitational waves at other frequencies. There are plans for a gravitational wave detector in space in the mid-2030s. This is a mission called LISA, and this is this pair of 3 orbiting spacecraft with lasers being bounced in between the spacecraft. And this mission will allow us to observe supermassive black holes colliding, which are going to have frequencies that are much, much lower, too low for us to detect using ground-based detectors. Next slide. Another effort is to observe gravitational waves using pulsars. So I won't spend too much time explaining this, but we can use radio telescopes to look at lots of rapidly rotating neutron stars. And by looking at how the pulses from those neutron stars fluctuate with time, we can also look for evidence of gravitational waves. And we expect that this collaboration, called the International Pulsar Timing Array, may have hints in the next few years of the detection of a combination of lots of gravitational waves from many, many supermassive black hole collisions happening throughout the universe, a so-called stochastic background of gravitational waves. Next slide. And then towards the end of the decade or into the 2030s, at some point we're going to have to replace the LIGO Virgo detectors with something better, just like we upgraded the Hubble telescope with the James Webb. At some point we're going to have to make a bigger, much more expensive version of LIGO, and there are plans underway to consider these projects. One is called the Einstein telescope, which is being pursued in Europe. That's going to be an underground detector that's going to be 10 kilometers long instead of the 4-kilometer LIGO detector length. And in the United States, we're investigating a detector called Cosmic Explorer, which will be above ground, which will be 40-kilometer long L-shaped device. But these are, for the future, after LIGO has done a few more years of observation. Next slide. Okay, so I think we learned a lot about gravitational waves. What's kind of the main thing I want you to take away from this? The main thing I want you to take away is, for most of our time observing the universe, we've been using electromagnetic radiation. Now we have a new tool available to us. In just the 5 years we've been using that tool, we've been able to observe more black holes than we have in the entire time we've been observing black holes, okay? And we're just getting started. So I think there's going to be a lot of excitement in this field in the years and decades to come. Thank you.